Welcome to this explainer. You know, when a crisis strikes and seconds literally separate life from death, there is one sound that instantly cuts right through the chaos: the wail of a siren. We see them every single day, weaving through traffic, lights flashing. But how often do you actually stop to think about the absolute marvel of engineering rushing past you? I mean, some of these things weigh over 14,000 pounds. Today, we are going to unpack the massive logistical and engineering hurdles hidden inside modern medical transport vehicles. Okay, let's dive into this. Because the vehicle you see out there on the street, it is so much more than just a truck with a siren and a stretcher in the back. Behind those flashing lights is this completely hidden world of immense structural calculations, secondary electrical grids, and cutting-edge medical environments perfectly tuned to keep people alive at 60 miles per hour. Let's peel back the layers and see exactly what goes into building one of these incredible machines. Here is our roadmap for today. 1. Classifying global emergency vehicles. 2. Hidden engineering and power demands. 3. Designing for ultimate safety. And 4. Matching platforms to missions. All right, jumping into Section 1, classifying global emergency vehicles. Now, what's really interesting about this is the core philosophical difference in how these vehicles are categorized across the globe. Take the U.S. classifications, like the KKK and CAAS standards. They focus heavily on the structural chassis construction. Essentially, they categorize by what the vehicle is. Meanwhile, across the Atlantic, the European EN 1789 standards take a completely different approach. They classify vehicles by their medical intervention capability, what the vehicle can do, scaling all the way up to the Type C, which is basically a full-blown mobile intensive care unit. Let's rapid fire through those U.S. classifications really quick. Type 1 features a totally separate modular patient box mounted right onto a light-duty truck chassis. It is perfect for heavy rescue, but, it's pretty bulky. Type 2 uses an unmodified standard commercial van body. You definitely sacrifice some workspace inside, but you gain immense maneuverability for darting through tight urban traffic. And then there's Type 3. It strikes a nice balance, using a customized Cutaway van where the front cab seamlessly integrates straight into that custom rear compartment. Moving right along to Section 2, hidden engineering and power demands. Think about this for a second. Adding hundreds of pounds of heavy medical equipment totally alters the vehicle's original center of gravity. Just imagine a paramedic having to take a sharp corner at high speed during a torrential downpour. It's a terrifying thought, right? Well, without rigorous weight distribution analysis and heavily upgraded suspension systems, that top-heavy box could easily roll over. Proper axle load distribution is absolutely essential here to prevent premature chassis fatigue and, most importantly, keep those tires firmly planted on the asphalt. And the engineering demands, they aren't just structural. They are deeply, deeply electrical. Standard vehicle alternators? No way. They simply cannot run defibrillators, ventilators, and secondary heavy-duty HVAC systems all at the same time. If they even tried, the engine would stall out or the life-saving devices would just fail. To solve this, manufacturers install an entirely hidden secondary electrical architecture. We're talking independent battery banks, high-output alternators, and deep-cycle batteries to guarantee stable, clean voltage delivery at all times. Plus, what happens when you mix high-voltage power with pure, pressurized oxygen? Yeah, absolutely nothing good. That is exactly why behind the fiberglass walls of the cabin, plumbers and electricians have to carefully choreograph their work. High-pressure oxygen cylinders demand incredibly reinforced mounting compartments, and the pressurized gas lines must be routed far, far away from any electrical wiring. This strict physical separation is a crucial safety compliance standard to prevent catastrophic fires if the ambulance ever gets into a collision. Which brings us to Section 3, designing for ultimate safety. At the end of the day, passenger safety heavily relies on the structural integrity of that modular box itself. Authorities mandate intense dynamic rollover crash tests for any new medical vehicle designs. To pass these brutal tests, manufacturers utilize rigid, extruded aluminum frames, so the compartment absolutely will not crush or lose its shape. And inside, traditional bench seating, which honestly is highly dangerous during sudden deceleration, has been totally phased out. Modern regulations require forward or rear-facing seats equipped with multi-point harnesses, keeping the paramedics securely restrained without ever blocking their hands-on access to the patient. Now, here is a vital safety feature you probably never even considered: sound. Manufacturers apply specialized acoustic damping materials right directly to the chassis floor. And this isn't just about making the ride a bit more comfortable. Excessive road noise and mechanical vibration severely impair a paramedic's ability to clearly communicate critical patient vitals to hospital dispatchers over the radio. A quiet cabin isn't a luxury.
It is quite literally a clinical necessity.
Let's say a deer runs into the road and the ambulance has to slam on the brakes to avoid an accident. So the crucial point is that crash safety regulations mandate extensive static load testing for all the interior hardware. Specifically, equipment cabinets must withstand an unbelievable 10G impact force. Without these massively reinforced mounting brackets, a heavy oxygen tank or a medical monitor could instantly break loose and become a deadly, high-speed projectile flying through the cabin.
Next up on the safety checklist is thermal control. Extreme climates dictate really rigorous insulation standards because vital medications and intravenous fluids will rapidly lose their efficacy if they get too hot or too cold. The vehicle relies on high-density polyurethane foam insulation and specialized HVAC systems that must strictly hold the interior between 20 and 25 degrees Celsius. And that has to hold true whether it's freezing in a snowy blizzard or absolutely scorching in a desert. Finally, for safety, let's look at how ambulances transport infectious diseases without spreading them. It all relies on the brilliant physics of negative pressure isolation. The ventilation system creates a very precise atmospheric gradient. Basically, air flows from the driver's cab into the patient module. It literally cannot flow backward. Then, before it ever leaves the vehicle, that potentially contaminated air passes through rigorous HEPA filtration, ensuring all pathogens are captured before the air is safely exhausted outside. It's a remarkably clever system.
Okay, wrapping up with Section 4, matching platforms to missions.
And this brilliantly illustrates the modern split in how fleets actually buy their vehicles. On one hand, you have a vehicle like the Geely Battery Electric Ambulance. It's custom-built for unpredictable urban routes, offering zero emissions, whisper-quiet transit, and way less vibration, which perfectly aligns with modern green municipal mandates. But then on the exact opposite end of the spectrum, you have the Ford T6 ambulance. With a rugged 4x4 layout, high ground clearance, and a massive high-torque diesel engine, this thing is specifically designed to crush unpaved roads and steep inclines for rural search and rescue operations.
But opting for an electric platform introduces a totally unique engineering challenge. High-draw medical equipment can rapidly eat up an EV's driving range. So, to solve this, manufacturers actually completely separate the primary drivetrain battery from the medical power supply. They use dedicated DC to DC conversion logic to guarantee that running a life-saving ventilator in the back will never, ever accidentally drain the motive power you actually need to drive the vehicle to the hospital.
Regardless of whether the vehicle is EV or diesel, though, there's one universal rule that applies to all platforms: payload capacity. It's strictly defined as the gross vehicle weight rating minus the curb weight. Fleet managers have to heavily calculate the weight of the modular box, all the hardware, the heavy oxygen tanks, and the personnel themselves. If an agency carelessly exceeds this payload limit, it causes severe suspension fatigue and terrifying handling instability on the road.
From the extruded aluminum framing protecting the paramedics inside to the sophisticated negative pressure systems keeping the air perfectly clean, it really is just incredible what is packed into these vehicles. The next time you hear a siren wailing and pull your car over to the side of the road, I really want you to ask yourself, will you just see a loud van driving by, or will you recognize the highly engineered rolling intensive care unit, perfectly adapted to its life-saving mission? Thanks for exploring this amazing topic with me on This Explainer, and I'll catch you on the next one.